Let's talk about some polynomial functions and rational functions. So starting with polynomials, there's not really a great deal of use of polynomial functions directly in a Calculus 1 course. You do need to know when you're running into a polynomial function. And a polynomial function qualifies as, or I should say, a quadratic qualifies as a polynomial, a linear is a type of polynomial, and also a constant function is a type of polynomial. So we've seen polynomials. It's just constant functions are considered degree 0 polynomials. That's the highest exponent is a 0. Linear functions are considered a degree 1 polynomial, the highest exponent being 1. And then quadratics are degree 2. When we talk about polynomials in general, we generally mean a degree 3 or higher polynomial. In Calculus 1, it often is the case that we really just need to know how to algebraically reduce with polynomials, be comfortable with expanding and factoring, and that's usually about it. So quickly here, the definition of a polynomial is any function that can be written in this form right here that you see highlighted. So there's one variable, x, a sub 0, a sub 1, and so forth. These are all constant values. They're referred to as coefficients. A sub 0 is called the leading term coefficient and is generally pretty important when it comes to determining some properties of polynomials. A sub n is called the constant term, so that's the one that is kind of the caboose of the train. And then n is the degree of the polynomial. So that's the highest exponent that exists on your variable. Now, we often use polynomials either in expanded form or in factored form. Factoring polynomials sort of depends on what its degree is. So if it's linear or constant, there's no such thing as factoring, like they're already factored. If the degree is quadratic, then you're using the factoring processes that you have learned for quadratic functions. If it's degree 3 or higher, then there's a separate set of techniques to work with. But if it is in factored form, it's easy to work with algebraically and makes it easier to identify the zeros. So in this factored form, these numbers right here are the zeros of the polynomial. So if you need to find the zeros or the solutions, it's very easy to do so. Okay, so let's talk about some techniques here. Now, when it comes to factoring polynomials, there is a generalized process, but we often don't need that generalized process in the example problems given in a Calculus 1 course. Oftentimes, there are shortcut methods to factoring degree 3 or higher, and that's what we need to be able to do. So for instance, one of the most common methods is, well, I should say apart from using the difference of cubes or the sum of cubes formula. So let me write those down real quick. So the difference or sum of cubes. This isn't used for this problem, it's just good to have. So it would be a cubed, let's say in this case, minus b cubed. So that's the difference of cubes. It's going to be a minus b times a squared plus ab plus b squared. Now, the form of this is actually pretty straightforward. It's just the original, well, the cube roots of the terms, a and then b. Then the squares of the terms, a squared and b squared, and then the product. It's usually the signs that are more difficult to remember. And there's a quick mnemonic, which is SOAP. And it goes like this. So this first sign over here is the same as the original. This sign is the opposite. And this last sign here is always positive. So if you needed a cubed plus b cubed, it would be a plus b times a squared plus ab plus b squared. Sorry, that one would be a minus because it's opposite. Now, that remaining quadratic, the a squared minus ab plus b squared, it doesn't factor any further. If it did, that would be part of the formula. So this is one way that you see cubic polynomials in a calculus class. Another is like this example. So I have this polynomial p of x, which is 4x cubed minus 3x squared minus 16x plus 12. Clearly, the difference and sum of cubes formulas would not apply in this particular case. However, there is a method of factoring this, which is called factor by grouping. And when you see higher degree polynomials, it will often factor by grouping. And what that means, I'm going to write it down. So factor by grouping. So what it means is you can take, say, usually you could just take the first two items, group them together with parentheses, and then take the second two and group together with parentheses. Now notice here I am putting a plus in between these two groups, and that's because the sign that's in front of a number stays with the term, okay? So I'm making this basically plus a negative 16x so that I can group the negative inside those parentheses. If I didn't, I would have to make sure I also changed the sign on the 12. It's a little bit more complex. So just leave the sign with the term. Now, within these groups, you should have some common factors. It's only going to work if there are some common factors here. So if there aren't, well then either you need to kind of like rearrange the terms that you grouped together, or it's just not going to work. But oftentimes it really does work just like this in Calc 1 examples. All right, so for instance, there's a common factor of x squared in the first set of parentheses, which leaves me 4x minus 3. And in the second set, there is I'm going to pull out a negative because in any polynomial, you really don't want a leading term coefficient to be negative. It just makes things more difficult. So I'm going to pull that out as a negative. And then also a 4 is divisible by those terms. So that would leave me with, again, 4x minus 3. So here's the thing. These two pieces match. And that's the key. Because now if those two pieces match, they are in of themselves common factors. And what you can do with common factors is you can group together the common factors as a term of itself, and then multiply that by the remaining factors. So if I take, for instance, from this first term, if I take 4x minus 3 out of it, if I divide it away, that is, it leaves me with just x squared. And then if I go on to the second term, and I factor out 4x minus 3 from it, it just leaves me minus 4. So then that right there gives me a factored form of this polynomial. Now, in particular, I can actually do a little bit better because I have x squared minus 4, which is the difference of squares, and you should know the difference of squares formula. The difference of squares, when you factor the difference of squares, it becomes the square root of the first term minus the square root of the second, and then the square root of the first plus the square root of the second. And now that thing is fully factored. We didn't have to go through a long process like you probably learned in a college algebra course where you need to list out the common factors of the constant, list out factors of the leading term coefficient, and then try different possibilities of quotients of those values. So that is the general method, but like I said, often in a calculus class, these types of examples are the ones that are chosen for the course. So as long as you can do that, the factor by grouping and then the sum or difference of cubes, you should be fine with factoring polynomials. Because at that point, if you need to identify the zeros, you can just set this all equal to 0, and then it's just like with quadratic. So you have the product of This is one number, this is another number, and this is a third number. So you have the product of three numbers where the product happens to be 0. What that means is either the first number happens to be 0, the second number happens to be 0, or the third number happens to be 0. So that would mean if I bring the 3 over, that would be 4x equals positive 3, or x equals 3/4, x equals positive 2, or x equals negative 2. So these are the factors, and these are the zeros. All right, let's look at some rational functions now. So rational functions, just like polynomials, there's not a lot that we have to work with in terms of rationals. We do need to know the algebra of rational functions. There will be times where you need to combine two rational functions together, which is going to involve finding common denominators and that sort of operation. Most of the time, you'll need to simplify, which means factoring polynomials in the numerator and the denominator, then canceling terms. Now, the one thing that I find students will often do, if they do make mistakes when doing that sort of thing, is they'll do things like this. They'll see, okay, there's a positive 2 and a negative 6. That divides out to, say, negative 3. So then they'll write this as like x over x squared minus x minus 3. And they say to themselves, yay, I did some math. Well, you did some math, but not really math that works. So here's the thing. These expressions, they don't really work that way. This expression in the numerator represents one number, so it's some y value. This expression in the denominator represents one number, and it is a y value to this function. And it just doesn't work that you can divide these y values in general. Okay? You have to identify if there happen to be shared factors. How do you identify shared factors? Well, the way to identify shared factors is to factor things. So, for instance, the numerator is linear. It won't factor. You just leave it as is. The denominator, however, it is linear. I'm sorry, it is quadratic, so it does have some factors. And if I factor it, this would be an x and an x. The 6 there can factor into 3 and 2. And then if the 3 is negative and the 2 is positive, the middle terms would add up to negative x. So now there's one number in the numerator. There's two numbers in the denominator. And in particular, one of those numbers in the numerator matches one of the number that's in the numerator. I think I said that right. One number in the denominator matches the one in the numerator. So they can cancel. You can cancel out those full expressions, but you can't cancel out individual terms within polynomials. Now, this right here would not leave anything in the numerator. So that often confuses students at first, and they want to just say like, oh, well, there's 0. Nothing's left here. But that's not the case. If you think about it, like if you had 2 divided by 2, that's just 1. Well, x plus 2 divided by x plus 2 is also going to result in 1 because, until you put something in for x, like let's say we put 3 in for x. 3 plus 2 is 5, and then 3 plus 2 in the denominator is also 5. So there's a common factor of 5 which cancels out to a 1. So there's not nothing in the numerator, there's a common factor of 1. The denominator, however, we don't have to put a factor of 1 in because there's also remaining factor of x minus 3 which we would leave. That's the kind of technique that you need to be able to do accurately. You'll do that a lot in a calculus course. Now, students will often get confused at algebraic steps and then wonder if they've done an appropriate step or not. So one thing that you can always do is ensure that you have done a correct step by using the graph of a function. Because here's the thing. If you've done an appropriate algebraic step, then the start of your algebra and the end of your algebra are going to be what's called algebraically equivalent. All right? And what that means is over this equal sign, we're saying that this function fully agrees with all the values of this function, except sometimes for like a finite few, okay? But in general, every single value of x plugged into here gives you the same y values of every single value of x plugged into here. What that means is you would have the exact same graph. So you can just use your calculator and determine if you have the same graph. And if you do, then that tells you that you've done your algebra correctly. So for instance, like if I come in and let me turn that off. All right, so the first function is x plus 2 over x squared minus x minus 6. And if you're unsure as to how to do parentheses in the calculator, if you have rational functions, just automatically put parentheses around the numerator and denominator, and that will solve like 90% of your problems. Okay. The other one is 1 divided by x minus 3. Okay, now in blue, I have the original graph. In red, I have the new graph. Well, sorry, my window, it needs to be reset. Tell you what, let me hit zoom 6 for the default. And it was quick, but you should see that there was the blue graph and then the red graph was mapped over top of it. They're the exact same graph. That's why you don't see a blue one right now. And that tells you that you did the correct algebra. Because let's say we did something incorrect. Let's say we made this, what was my original thing? I think I said x divided by x minus, it was x squared minus x. And then there was a minus 3 on the outside. Okay, so if I graph these two, I get something completely different. They're not the same function. You did some incorrect algebra. And, you know, if your class, if you're not allowed to use a calculator at different places in the class, that's fine. You can always use a calculator in the homework while you're practicing stuff, and you can kind of check yourself. You know, try some algebra, and then see if that is permissible, you know, while you're doing the homework. Okay. Let me go back to a couple other details here. So there was some additional things that we needed to know about rational functions, like how to find x-intercepts and y-intercepts, locations of vertical asymptotes, and locations of horizontal asymptotes. All right, so I've given you what you need for the algebra for the most part, but these other things are important too. Locations of x-intercepts, happens whenever the numerator has zeros. So for instance, in this particular equation here, this would be where the numerator has zeros, so you would just take x plus 2, set it to 0, and that would give you x equals negative 2. All right, and that's that. Locations of y-intercepts occurs where the ratio, at the ratio of constants. So the ratio of constants, if you take the ratio of 2 divided by negative 6, you would have a y-intercept located. Actually, I'll write it as a point. So 0 for the y, and then when we let 0 for x, and when we let x be 0, the function evaluates to 2 over negative 6, which is negative 3. So this is effectively the y-intercept, so negative 3. Locations of vertical asymptotes. So that is where the denominator has zeros. So originally, this particular function looks like it has vertical asymptotes where x squared minus x minus 6 is equal to 0. The thing is, it's not entirely the story. It's where the reduced function has zeros in the denominator. So it's actually just this one over here. So it would be where x minus 3 equals 0. So you have a vertical asymptote in this function at positive 3. Negative 2, so when I set x plus 2 equal to 0, negative 2 is a special thing. This is a hole in the graph. And a hole in a graph kind of looks like, you're graphing it, you come across a point that just doesn't exist. All right, so that's a hole in the graph. And so those happen whenever you have a shared factor in the numerator and denominator. All right, so that's basically what we've shown in this particular example. Horizontal asymptotes, you just compare the degrees of the numerator and denominator. All right, and when you compare the degree of the numerator and denominator, either the function is top-heavy, which means you have a higher degree in the numerator, and therefore there's no horizontal asymptote. All right, or it's bottom-heavy, so you have a larger degree in the denominator, so therefore you have a horizontal asymptote at 0, y equals 0. Or they're equal, so the degrees are equal, then you have a horizontal asymptote at the ratio of the constant terms. Okay, so let's look at all these things for the second one. All right, so for this second one, you should always check to make sure it's not reducible. So try to factor if you can. So this one's a little bit more difficult factoring, but that's okay. So 3x and x would give me 3x squared. 1 and 2 would give me 2. So the middle term here would be 1x plus 6x, that would be 7x, or 5x, so that wouldn't work. If I swap these two terms, 2 and 1, that would be 2x and 3x, so that would be 5x or 1x, so that doesn't factor. Okay, so this means this is the reduced form. All right, so, well, actually, if it doesn't reduce, then the vertical asymptotes are going to be trickier. That's okay, we'll go with it. All right, so x-intercepts. You just look to where the numerator is equal to 0. So that's going to be at x equals 1. So you just set the numerator to 0 and solve. It should be written as a point, so it would be 1, 0 technically. All right, y-intercepts. That's another easy one. You look at the ratio of the leading term coefficients. So that would be negative 1 over 2, which is negative 1/2. And written as a point, it would be 0, negative 1/2. Okay. Then horizontal asymptotes. The horizontal asymptotes, what you do is a similar thing to the y-intercepts. You look at the degrees. So the degree of the numerator is 1, the degree of the denominator is 2. So this is bottom heavy. And if it's bottom heavy, there's a horizontal asymptote at y equals 0. If this was x squared minus 1, then we would take the ratio and the y-intercept, or the horizontal asymptote would be at 1/3. All right, the vertical asymptotes, I'm just going to skip because it's the zeros of the denominator. It doesn't factor, and so we'd have to use a quadratic formula. I'm not going to go into it. You wouldn't have examples like that in the class. Generally, you have things that just, polynomials that just factor in this course. All right, moving on. Now, some things that we would use polynomials and rationals for are inequalities. So we need to make sure we know how to solve equations and also inequalities. There's linear inequalities, and then there's the rest of inequalities. And the linear inequalities are the easiest. In order to solve linear inequalities, you basically just follow the principles of solving equations. So for instance, if I have this as my inequality, all right, I can add or subtract any value I want to both sides of an equation or inequality. And then the next step, I would need to get x by itself, and to do that, I would divide through by a negative. The one thing about inequalities is that if you multiply or divide both sides by a negative, you turn your inequality around. So this would actually be x is greater than -1. That's the only thing that's different from solving linear equations. You will definitely run into times where you need to work with inequalities that are linear, especially involving absolute value. Now, to do this, you take out the absolute value by splitting this into a trilinear inequality. So you just take what's inside the absolute value, put it in between the positive and negative of whatever this is over here on the right-hand side. If it's a constant, fine. If it's an expression, that's fine as well. But you just set it in between those terms, basically. So you're saying you want to know where 3x minus 2 is greater than -5 and less than 5, right? And the reason for that is absolute value, its graph is like a v, all right? And then a constant function 5 is kind of like this. And if you want to know where the y values of this function are smaller than the y values of this function, then it's going to happen along two different lines. So you kind of have to solve for both of those lines. So where the line is negatively sloped, like here, or positively sloped right there. So that's basically what we're doing here, okay? So that's the idea. When you do that, you solve it just like a regular linear inequality, but you just work with all three sides at the same time. So like you can add 2 here, which would result in you adding to 2 to all sides. So this would be -3 less than 3x less than 7. And then if you divide everything by 3, that's fine. This is a positive number. It doesn't change the direction of the sign, so that would be -1 less than x less than 7/3. And so that would be the solution to your inequality. So you'll run into that, that's a good thing to be able to do. When it comes to quadratic or polynomial or rational inequalities, things get a little bit more difficult, all right? Because when it comes to the graph of something, a quadratic has this U shape to it. And if you're trying to figure out where, a graph's y values are smaller than some constant or some other function, it doesn't really matter. There's different possibilities for when that can happen. And so you need to basically find out where these things intersect first. So find out where the curves intersect. And then on each interval, so like this is one interval here. This is a second interval here. And this is the third interval here. And then on each interval, figure out which function is higher and which one's lower. And then answer based off those intervals. It's the only way of doing these things. It's just what you have to do. So it kind of changes how you go about solving these. Now, it is true that you want to know where your functions have zeros to start with. So for instance, this one, if I want to know where x squared minus x minus 12 is less than 0, I would begin by factoring it so that I can see where the function is 0, right? So x, 3, 4, that's a negative and that's positive. All right, so I have zeros at -3 and +4. So those zeros, -3 and +4, are effectively where this function and this function intersect, okay? Now, I want to know on each interval which one is the larger one. All right, so basically, since I have this set to 0, I just want to really know if this function on the left-hand side, I'll call it 1, is positive or negative. So I'm just going to plug in a number say from the first interval, which I'll just choose maybe -4. On the second interval, I'll choose 0, and then on the third, I'll choose 5. So I'm picking some value within those intervals to test to see which function is higher or lower. Now, if I put -4 into this function, -4 plus 3 is -1. -4 minus 4 is going to be -8. Well, a negative times a negative results in a positive. So it tells me that this function is positive on that interval. So that's not part of my solution because I'm looking for things that are negative. All right, if I put in 0, all right, so 0 plus 3 is 3. 0 minus 4 is -4. 3 times -4 is a negative value. And then lastly, coming over to the 5, 5 plus 3 is 8. 5 minus 4 is 1. The product of those two is positive. So that tells me that the interval that is negative is my solution. So the solution to this is the interval from -3 to 4, and I'm not including the endpoints because it is a less than instead of a less than or equal to. All right, that's more difficult than the linear inequalities, but that's just what you have to do. Let's try a polynomial inequality. So we're trying to see where this curve is less than or equal to this curve. Now, an easier equivalent statement is to determine where, bring that over as positive x and positive 4, is to determine where this is less than or equal to 0, because I just want to know if it's positive or negative. It just makes the test in the end easier to do. So we'll go with that instead. All right, so factoring, I should be able to factor by grouping. So if I take x squared out of the first two, that leaves me with x plus 4. And then there's no common factors in the second two, but that's okay because it's already x plus 4. So then if I pull out the x plus 4, that leaves me with x squared plus 1 less than or equal to 0. All right, now the zeros here, the only real 0 I have is at -4. It looks like I might have zeros at like plus or minus 1, but this is the sum of squares and not the difference of squares. If it was x squared minus 1, then I would have positive and -1. But technically I've got positive and negative I, which is that complex unit. And the thing is, that's not a real number, so I don't need to put it on the real number line. So this is a real number line, which just means you don't put complex numbers on it. All right, so I only need to test this one value. So the intervals, I could pick something, say at -5, and 0 looks easy. All right, so if I put -5 into, just pick the simplest expression you can, plug it in here, that would be, let's see, -5 plus 4 is -1. 5 squared plus 1 is 26, so everything's negative on that interval. If I put in 0, that would be 4 times 1. Everything on that interval is positive. Now, I'm looking for where this thing is less than or equal to 0, so I want it to be negative. So this is my interval right along here. It's less than or equal to, so I need to include. So my solution here in interval notation is -infinity to -4 inclusive. All right, last one, hardest one, but we're going to do it. This involves rationals, and in particular, I'm going to have to do some algebra with rationals. I told you that you might have to do some occasionally. It's not something that is something that we always have to do, but you might have to do occasionally. In this particular case, I need to set this thing to 0 because it's a whole lot easier to determine where a function is positive or negative rather than comparing where one function is bigger or smaller than another function. So I'm just going to subtract that whole thing over, all right? Now, I need to have this in a factorable form, which means I've got to combine it into a single rational expression. So to do that, I need a common denominator. So what I'm going to do is I'm going to multiply the denominators together. Whoops. All right, the first expression, in order to get it with the common denominator, I need to multiply the numerator by x minus 1, the other denominator. In the second expression, I need to multiply the numerator by x plus 1, so this will be 2 times x plus 1. Okay, I've got to do some algebra in the numerator, so let's see, that would be x minus 1 minus 2x minus 2, which would be x minus 2x is negative x. Negative 1 minus 2 is minus 3. So I effectively have negative x plus 3 over x plus 1, x minus 1. I want to know where that's greater than 0. Now, the only thing that's different about rationals from polynomials or quadratics is that you have to consider the zeros of the denominator as well. So the thing can change sign over an asymptote as well as an x-intercept. So my zeros here, I have one at negative 3, that's from the numerator, negative 1, which is an asymptote, and then positive 1, which is an asymptote. So these are my intervals, and I just need to pick some value within each interval, so say negative 4, how about negative 2, 0, and 2. All right, so if I put negative 4 into my rational, it would be negative times negative 1 all over negative 3 times negative 5. So that's 4 negatives, so everything there is positive. If I plug in negative 2, it's a negative times 1 over negative 1 times negative 3. So that's 3 negatives. That's going to be a negative. I put in 0. I have a negative, a positive 3, positive 1, and a negative 1. So that's positive. And if I plug in 2, I have a negative, a 5, a 3, and a 1. So everything there is negative. So I'm looking where things are greater than 0. So I want this interval here where that's positive. And then I want this interval between here, which is also positive. So my solution in this particular case is the interval from negative infinity to negative 3, and then from negative 1 to positive 1. Now, the only last piece of contention here is if this happened to have been greater than or equal to 0, I would have been able to include the negative 3, but I still could not have included the negative 1 and the positive 1. You can include asymptotes. You can include zeros, but you cannot include asymptotes as part of your answer. You get division by 0. They don't exist in your solution. But that didn't apply in this case, but just so you know, to watch out for that sort of thing.